Hi, this is Kaylee, and I want to talk a little bit about gravity, circular motion, and its relationship to astronomy. Now, this is what we call the universal law of gravity. Now, that's a little bit of a misnomer. A lot of times now we call this Newton's law of gravity, because Einstein, with his general theory of relativity, has kind of made a correction to this. But we still use this. It's still very effective. Only time where we really need Einstein is when we have something moving very fast or something that's near something that has a lot of gravity. So, but as far as like general stuff out in space, this still works fine. But I want to relate it to something. So, when we normally talk about weight on the Earth, we have a tendency to use this equation, Fg equals mg, where g is the acceleration due to gravity on the Earth, which is 9.8 meters per second squared, or sometimes people will put it as 9.8 newtons per kilogram. Either way works fine. But both these are equal to the same thing. If we put the mass of the Earth, our mass in there, and the radius from the center of the Earth to the center of us, which is pretty much just the distance from the center of the Earth to the surface of the Earth. The height of a person doesn't make a whole lot of difference with that number. That should equal, when we just do the mass of the person times 9.8. But what if we want to figure out the acceleration due to gravity on another planet? Well, that's where we can actually combine these two to actually come with that. Again, remember, we're going to call this m2 the mass of the person or the object, and this m is the mass of the person of the object. So if we combine these two, we get something that looks like this. Let's say mg equals g m1 m2 over r squared. But we just said that this is the mass of the person or object, and this is the mass of the person or the object. So those two are really the same thing. So that's really an m2. Well, since m2 is on both sides, they can cancel out. And we just get the acceleration due to gravity on anything is equal to the universal gravitational constant, the mass of that object, so the Earth or the Moon or anything like that, divided by the radius of that object squared. So using that, you can figure out the acceleration due to gravity on any object as long as you know its mass and its radius. So there's a very good use of algebra. But let's expand this a little bit. Okay, let's see what else we can do with Newton's law of gravity. So we've got Fg equals g m1 m2 over r squared. And if we think about the Earth-Sun system, so one of these masses is the Sun, the other mass is the Earth, and r is the distance between the center of the Sun and the center of the Earth. That force due to gravity is causing the Earth to go around in a circular orbit. So that force can also be renamed as a centrifugal force. So Fc equals mac, where in this one, that mass is the mass of the object going around in a circle. So if we said m2 was the Earth, and the Earth's one going around in a circle, then that would be a m2. We'll just label that just to keep track of it. But again, gravity would be that centripetal force. So we can set these two equations equal to each other. So g m1 m2 over r squared equals m2ac. Well, m2's on both sides, so they kill off. And so, well, that's okay, but let me do something else. We know the centripetal acceleration is equal to v squared over r. So we can substitute that in. So g m1 over r squared equals v squared over r. Okay. Well, that's a little bit interesting. But what else can we do with it? Well, velocity is equal to 2 pi r over the period. Substitute this into there. Now it's squared, so v squared would be 4 pi squared r squared over t squared. So we plug that in, gm1 r squared equals 4 pi squared r squared over t squared. Well, that's also over r. So if we simplify that, it really looks like this. 4 pi squared r squared over r t squared. A lot of letters there. But the cool thing is that r cancels out one of these. So let's rewrite that and clean it up a little bit. So we've got gm1 over r squared equals 4 pi squared r over t squared. And so let's say I want to solve this for r. So let me move this over. So we get gm1 t squared, because I'll move that up, move this over, equals 4 pi squared r, and that would be cubed. And let's say I want to continue solving for r. And so I want to come over here with it so I have enough room on my page. And so I would get r cubed equals, that would divide, so that would be gm1 over 4 pi squared period squared. This is actually a pretty famous equation. This is called Newton's correction to Kepler's third law, where Kepler's third law is this. It's a cubed equals, or approximates, t squared, where Kepler used a semi-major axis because Kepler knew the orbit was actually an ellipse, not a perfect circle. And so A is what we call the semi-major axis, which if we have an ellipse, they don't have an exact center, they have two foci. But A is the semi-major axis, so that's from the center part to the long side of that ellipse. Is proportional to the period, in other words, the time it takes the planet to go around, squared. And he also came up with a new unit called an astronomical unit. We just call it an AU. And that's the average distance between the sun and the earth. Because he didn't know exactly what that was, so he just said, that's going to be my measuring stick for the solar system. And so he came up with this after doing loads of geometry. This, when we throw some physics and some known expressions in there, is a lot easier to work out. But the cool thing is maths of the object that planet or moon's going around is still in the equation. So we can use this equation to actually find out the mass of the object that's causing something else to orbit it. So if we did this with, like what we said, the Earth and the Sun, put the radius of Earth's orbit in there, the time it takes the Earth to go around the Sun, we can actually calculate the mass of the Sun. So let's try that. I've got some numbers over here, and G is 6.67 times 10 to the 9 minus 11, and these are the units. Now, if we just take this and plug them in, like I want to actually solve for the mass of the sun. So let's rearrange this to solve for the mass of the sun. So we'll pull those back out. So M1 would equal, these will go up, so that'll be 4 pi squared r cubed. and that will go down, G, and that will go down with it. So rearranging, we get this equation. Now we can plug our numbers in. This is an advantage of solving things algebraically before you throw numbers in it, is that you can get it down to you just have to use the calculator once. So M1, or mass of the sun in this case, will be equal to 4 pi squared R, which is, we're going to use this one. Now, astronomical unit is not exactly 1.5 times 10 to the 11th meters. It's actually a little bit more, so I've rounded that off to just those two positions. That's got to be cubed over 6.67 times 10 to minus 11th times period, which we're going to use 365 days. But here's the thing about this. We can't use days in there. We actually need to use seconds because we got to get everything in standard units. So 365 days, which is not exactly, it's 365 and a quarter, but we'll just estimate. One day is 24 hours, and 1 hour is 60 minutes, and 1 minute is 60 seconds. So if we take all that, 365 times 24 times 60 times 60, we get that 1 year is 3153600 seconds. Oh, that's a lot of seconds. So we'll put that in, 3153600, and that's got to be squared. Wow. So now we just have to do this mess, and we should be able to figure it out. All right, so the mass of the sun would equal, bringing my trusty calculator back out. So 4 times 3.14 squared times 1.5 times 10 to the 11th cubed divided by 6.67 times 10 to the negative 11th divide by 3153600 squared equals 2 times 10 to the 30th kilograms. And if you actually look it up, that's pretty close. So even with me rounding some things off, with this, we still get within a good ballpark measurement of the mass of the sun. Now we can take this, and any time we see something orbiting something else, so it doesn't matter if it's the Earth and the moon going around. So any time we find something orbiting something else, if we can figure out that radius and the period it takes for it to go around, we can actually figure out the mass of the object in the center. So that's how we can figure out the mass of something like Jupiter or another star or anything like. If we can find something that's orbiting it and measure that radius and measure that period, we can determine the mass of the object that's going around. Matter of fact, that's how we can determine the mass of something like a neutron star or black hole. We look for something that's going around it, use that orbit, and the time it takes for it to go around, and we can actually figure out the mass of that object. All right. Hope you enjoyed this little bit of math magic where we combine those two things, circular motion and gravity. And now you know a little bit more about how we figure things out in space. Thank you. Talk to you again later.